Okay, so I want everybody to close their eyes and envision um envision a like a mountain, like one that you would go to like a natural park and you would go hiking, say, on this mountain. Okay, and then what's gonna happen is when you do a hike on that mountain, you're not like walking on every single point of the surface of the mountain. That's not the point of the hike. The point is you have some sort of a path, right? Some kind of, it's like a loop-de-loop hike to go around on this surface. So that you start in the same spot, and then after you do the hike, you end up back at your starting point. So far, so good?
Yeah.
Okay. So what I want you to think of is if you were looking from top down, so you're looking from the top, you're looking down at the mountain, and if you were to you were making a map for this hiking trail, and you were to just trace out that curve in the XY plane of what that hike looks like, regardless of what your elevation is at any point. Just the XY coordinates looking top down onto your hiking trail. Okay. So that hiking trail is going to have its own kind of extrema involved. So if you step back and you look at the entire mountain or whatever you're doing, that mountain has its own absolute maximum. It has its own extrema. But when you do this hike, you're now restricted to that specific trail. And that specific trail in itself is going to have its own constrained extrema. So that are not necessarily the extrema of the mountain per se, but if you take that mountain and then restrict that mountain to your hiking trail, you can get a different kind of extrema. Now you can restrict essentially your surface, the mountain, to the hiking trail that you trace out. So far, so good. So that's kind of this idea is we can have extrema for surfaces in general, but then if we constrain a surface to very specific curve in its input space, then that specific curve in the input space will constrain various values of the function that you're going through, and then you can identify extrema on the constraint. Make sense? So we're going to take a look at some very excellent and eye-opening artistic expression here. So here's x, here's y. Here's how I'm going to try to show you this. So suppose we have, this isn't going to be a mountain. I'm going to do a different shape. Well, let's make a parabola, say. But instead of it being centered at the origin, I'm going to shift the paraboloid over some. And so this is going to open upward like this. So this would continue up, and then obviously it's rounded out. Okay. So here's our z-axis, so that we can see that we've shifted off of the main axis. And so this right here is the surface. So we would say z is equal to some function that takes in x and y familiar. We've been doing this for the last 2 weeks or so. Now, the idea is, what if in the input space, I decide, so if this is going to go back, that's not going back. Can you see can you orient yourself three-dimensionally here on the whiteboard? So if we have some sort of constraint curve, maybe that goes like this, and it goes back into there, and then maybe it comes around, but it forms this closed loop, right? So this is a constraint curve C. But if you were to look top down at this, if you were to look top down at this in the input space, x is y, it would look kind of like, so x a little bit and positive y, so questionably accurate depiction of what's happening. But you see, so you're looking at your curve C, and we notice that C here is actually just in itself some g of xy equals to 0. So implicitly defined function in the xy plane. But it's underneath a surface z of fxy. And if we're going to constrain the parabola, I'm going to pretend like we're tracing, so it's like tracing the function values of what this would be kind of cut out from the parabola. You see that? So this could be like the front side maybe, and then like behind you're cutting out. And so here we know that the paraboloid in itself doesn't have like a singular absolute max, because this is going up to infinity. However, if we constrain the surface to this particular path, like if we could figure this is like our height or like a roller coaster track, this does technically have a maximum. It has an extrema relative to our constraint. And this could be considered the maximum value that we can achieve on this surface when we're constraining it on this particular track. So we're choosing a very specific set of points in its domain, and then looking at the biggest possible value. And then its minimum here could be like down here, right? So that's occurring. This input point be like this input point. So I know it's a little bit difficult to see, and that's why the textbook is going to be really, really helpful for getting better graphics, basically, on what's going on here. But I wanted to be able to draw this so that at least you get a preliminary idea of all the algebra we're about to be doing. Because it gets very, very just technical at a certain point, and so it's easy to step away from this idea. But this is ultimately, at the end of the day, all we're doing. We're saying, can I take a surface that's given as z being relating to two variables, and then can I go into my input space, constrain a specific implicitly defined level curve, gxy is to 0, just sticking it onto there. And then if I only took those points from the domain and then see which surface values we get, what's going to be the biggest, what's going to be the smallest. That's it. Okay? Thumbs up. That's good. So that's all we're doing today. The nice thing is there's really only one big theorem, and the rest of it is procedural. You're good to if I erase?
Yeah.
Okay. Oh, wait, I should have. You have the picture in your notes. Well, and if you don't have the picture in your notes, you have the textbook. Okay. Here.
Picture in my head.
We call this parallel gradients. Also called the ballpark theorem. Not like guessing within the ballpark, but like a literal baseball field. Sometimes when I see the names of these theorems, I think it's kind of like when the older generation tries to catch up to the next generation's like lingo and stuff, but then like doesn't quite apply it exactly the same way, so then it just looks kind of corny. But yeah. So
What teacher
that.
means?
The what?
What teacher means?
Yeah, I think I feel like I keep my meme information up to date because I teach high school students every summer, so it gets refreshed. But they're putting out new garbage at a rapid rate. Last few years. Okay. So f is going to be a differentiable function. Differentiable function in a region of R2. So that's basically what we just drew. That contains the smooth curve, and we're going to call this curve like we did. We called it C, and the colon means C defined by or as given by g x y equals 0. So that was like the specific constraint, or like the hiking trail. And so we're going to assume that f has a local extreme value. So it doesn't matter if it's a maximum and just a local extreme value on C. In other words, it'll correspond that when we constrain this, there's going to be a tallest point, that's going to be the lowest point on your hike or whatever. At a point, and we'll just call it P. And so we need to know it's in the input stage. So then, when we take the gradient of the original, so think about this like the mountain. The gradient of the mountain at the point is going to be orthogonal to the line tangent to our constraint C, specifically at the point of interest, that point where there is that extreme value. And then the last assumption we want to make here, so assuming that the gradient of G at your point is not the zero vector, it follows that, do you guys remember what this math symbol means? Yes, so there exists. There exists. There exists some constant real number lambda, which we call a Lagrange multiplier, the name of the section. Lagrange.
That's the name of this section 15.8.
Lagrange multipliers. So that's the character of today's episode. And then such that the gradient of f at our point can actually be expressed as some scaled version of the gradient of g at the point. In other words, they're parallel. So if you have two vectors, I give you some vector. So this is my gradient of f at some p. And if I have another vector that's maybe not the same vector, but like this, and that's like the gradient of g at p. That was terrible. The gradient of g at p there. They're not the same length, but they point in the same direction. And the analytical way that we express that is simply saying that this vector is actually the same vector. It has the same direction. We just change its magnitude by some scalar quantity. It's like scrolling it up or down. And I think a reason why this can be confusing is simply forgetting that the gradient is a vector. So by definition, the gradient is a vector. The gradient is a what?
Vector.
A gradient is a vector. So this equation is indicating, I want you to think about it almost as in when we were talking about vectors in chapter 13, like u equal to some constant times v. Well, if you saw that, you'd be like, okay. Well, these have the same direction because the only difference is I just multiply by c. But here, suddenly everyone freaks out. They're the same thing. Except for now we just happen to call this vector the gradient of f at the point. We just happen to call this constant lambda down. And for context, and we also just happen to call this vector this gradient. It's a vector being equal to another vector with the same exact direction because all we're doing to change it is change its magnitude. Thumbs up, that's good? So this in English, you would say such that they're parallel. So there exists a Lagrange multiplier so that the two gradients are parallel. So if you see those English words and then you suddenly see this in math, that's the same thing, okay? Because this is a gradient is a what?
Vector.
So that's the vector. Same exact direction means parallel, especially if there's only a constant multiple in between. Okay?
So lambda is always a constant.
Yes, because we're given definitionally lambda is some real number. Okay. This is the one case where the visual intuition, in my opinion, is more confusing to the concept than actually the proof. So we're gonna go over the proof, not in its full rigor. Okay, we'll do like. So there's only a few computer science people in here, but it's the difference between like pseudocode versus like the actual code. So we won't do like the actual code, like the full formal rigor, but we'll outline the logical process that goes into showing these things to be true. And that'll give a good picture of kind of the step-by-step mental map so that you can make it make sense for yourself. Because that was a lot of words, and that was a lot of, random symbols. And so what does that actually mean? And it's guaranteeing, essentially, a way for us to identify extrema using gradients instead of having to do some other clunky analytical method. So it's easier to compute a gradient and to then do a system of equations than it is necessarily to have to guess and check an infinite number of points. Yeah. So we were given that C is smooth. Now, you don't need to know what that means to this class, so I'll just tell you what that means. Being smooth here in this specific context of what we're doing in Calc 3 with R3 is we can define our curve. Normally, we gave that by gxy is 0. But that means we can just parameterize it in the xy plane to some vector r. So r of t is some x of t and some y of t. Where we're gonna have that x and y are differentiable. That's important. And on top of that, they're going to be differentiable on an interval in this this parameter variable t, and t is containing some t naught, with the point at the extrema, so PAB, can be found as x of t naught, y of t naught. Does that make sense? So if I parameterize it, and then I choose specifically a t naught, some specific time at which the x coordinate changing as a function, but as soon as I plug in t naught, that's equal to a, and then y at t naught is equal to b, where specifically this is where the extreme values occur. Okay, and so what we're going to do is, if you think about it, as you're going on your hike, you're actively changing your altitude. You're changing how high you are depending on where you're at on the hike. And so that's just change. Change of what? Well, you're still technically changing on the mountain, the original surface. So we're looking at a rate of change as in a derivative of the original function, but now with respect to this new parameter time as you're walking around. So what's going to happen is we're going to vary t and follow t. So if you're a law-abiding citizen, when you go on a hike, you stay on the trail, basically. I know that's something that Bella would probably not agree with. Say, search after what, the praying mantis or something. By the way, I read all the little comments you post on there, like when you submit your labs. There's some real funny things I read in there every week. Anyway, so we're taking a rate of change of the function with respect to this new parameter time, instead of doing, so now think about this. This is a partial derivative where the intermediate, so the x and y are now actually the intermediate variables where t is the singular independent variable. So we want to take the partial with respect to f partial x times regular dx dt. And then what's the next component?
Partial f over partial y.
Yeah, partial f partial y times what?
dy dt.
And then, as any good math textbook would say, it is obvious that this is equal to the gradient of f dot product with r prime of t. Actually, in this case, I would agree with the textbook. It is obvious that.
Yeah, and usually it's like after 12 steps of kind of complicated algebra, and it's like, it's easy to prove, and I'm staring at it for 10 minutes.
Yep. That's. But do you guys see where this comes from? The gradient of f, remember, is the partial, so the x component is fx, the y component is fy. And then since we defined r of t to be x and y, and so when we just simply differentiate r prime, that gives us x prime, y prime, or in other words, dx dt, dy dt. And that dot product is taking your x components, pairing them up, and then taking your y components, pairing them up. So that's just a little dot product going on here. So the key is making that observation. And once we do that, that's pretty much, I mean, that's the main thing here. And so recall that at at this specific point, x t naught, y t naught, this is where the extreme values occur in, right? So this is our point AB, where f has an extreme value, has an extreme value, we have that. Now, recall, calc 1, if you are at an extreme point, what is the derivative supposed to be equal to?
Zero.
Right, you shouldn't be changing at that instant. And so, df dt should be what? Yeah, specifically when we evaluated at this point, t is t naught. Make sense? So if we're told that this is where the extreme value is happening at t naught, then df dt, if we're going to put that at t naught, needs to be 0. So all we got to do is put that into math symbols. We say df dt. If we put that at t is t naught, that needs to be equal to 0. Otherwise, this isn't actually an extreme value. So that tells us something though, because df dt is actually, we can write it in terms of this really handy dot product. So it's really the gradient of f at our point AB dot r prime of t naught. Do you see why I need to distinguish? This needs to be with respect to a and b here, whereas this one needs to be t naught. Okay. That means this is 0. Now, all the way back to like week 1 of class, okay? Dot product is equal to 0. What does that tell us about the vectors? They're orthogonal. Cool. And on top of that, we know something else. Specifically, we call that this. If we're given some vector valued function r, and then we call this what? Not the derivative, but the tangent vector, right? So this is the tangent vector. And so the gradient at our extreme value point is not orthogonal with C itself, but it's orthogonal with the tangent line at C. So if this is like your curve C, so if I'm looking down, top-down view again, x, y, and suppose we have some C, okay? So this is our C, and we parameterized it to R, and then R prime is giving the slope essentially at an instant. So like right here, the slope at this instant is like that. And so that slope, that tangent vector, R prime, or I could think of it as a literal tangent vector, R prime, that's what the gradient is orthogonal to. And it's going to be orthogonal to the gradient. This will be gradient. So that's why we have the gradient lining up like that, specifically at extreme value, because definitionally, or well, not definitionally, by the theorem, we know that we can't have any change whenever we're at an extreme value. And so it so happens that because this dot product is how we're changing, that dot product being 0 is going to be orthogonal. So it marries together calc 1 stuff with then what we know about just vector arithmetic. Okay, so from all of this, we basically conclude this is going to be orthogonal. So we've proven the first part of that here. Good? Okay. And I'll run through the, I could fit it under here. So if we have, now we're going to prove the other little thing. Is that if we had C as being G, X, Y is 0. This is, by definition, is a level curve of, if we turned it into Z equals G, X, Y. Right, so if you were to make it G, Z equals G, X, Y, then restricting it to G, X, Y is 0 in X, Y, that's just a level curve. And so, the gradient G at the point will be orthogonal to C. And do you understand why that has to be true? We're basically just taking another surface and then taking its gradient at a point where we know there's an extreme value. So for the same reasons that we just argued, it's going to be orthogonal again. So we can cite that word. And so this is going to tell us that the gradient f a b and the gradient of g AB are parallel. If they're both, say, here, and that's the gradient of f, but then we take the other level curve, and that's the gradient of g, well, then they're in the same direction. They're both, if they're orthogonal to the same exact tangent vector, then they're going to be in the same direction. And so this English word parallel is the way that we can say with words the math language of there exists a lambda in R such that gradient FAB is a scaled version of the other vector, which is the gradient of G. And that's it. Tentatively a proof. Obviously not entirely formalized, but that would be a great outline to follow, logically speaking. Okay, so thumbs up if you get an idea of first just like the physical application of what's happening. And then thumbs up if the reason why the whole parallel stuff actually has to always work, because of the dot product.
Actually, wait. In the top line on C, is that one also R prime? The one where you have DF? Sorry.
Oh no, that's a good question. So here I'm emphasizing the tangent behavior here, but in reality, what's going on is it's just the tangent vectors.
Right.
Yeah.
And so.
So in this case, I could just get rid of that. And that would be R prime.
Right. And so that would also be R prime. So they're going to both be orthogonal to R prime. And the difference between gradient of f and gradient of g is the constant lambda.
Yep.
Right. I might understand this.
Yeah, nice. And this is where you really see how Calc 3 it feeds on itself. Chapter 13. Differential, so chapter 15 and 14. Interval on a point parameterization, Calc 2. Chain rule, chapter 15. Gradient, chapter 15. Tangent vector, chapter 14. Dot product, chapter 13. Extreme value, Calc 1, Calc 2, Calc 3. Evaluating a derivative at a point to 0, Calc 1. Dot product, Calc 3. Tangent vector, chapter 13. So yeah, you use everything. Cool. All right. You want to see a problem? The calories from that burrito are finally kicking in. So I'm like, okay, I'm awake now. Okay. There is a procedure that now that I'm looking at it, now that you've seen what's going on, this is just a waste of your time. So I'm not going to show you that. I'm going to show you the equations that are important. But basically, if we're saying, oh no, I'm going to put this in the star. So if we're saying that they're parallel, so a gradient is a what?
Vector.
Good. So this is saying they're parallel. So this is how we set up a Lagrange multipliers. It's that equation. 3 things. Very, very challenging. Okay, now each one of these things can be broken down. So the idea is if you have a gradient, then if I say that the gradient of f xy is equal to lambda the gradient g xy, what I'm really saying here is I've got a vector because a gradient is a
Vector.
and so what are the components of this particular vector?
The partial.
Right?
What is the thing? Oh, yeah.
Okay, so then lambda times what?
Yeah, the star. Using the left or partial.
Yes.
You need to know.
I can just
It's
do this.
important.
So what we've done is we've effectively created a
Same.
system of equations. Because we
And
have equation 1 is going to be
Is
fx is equal to lambda
different from this?
gx.
Let's save it.
Equation 2 is going to be fy is equal to lambda gy. Now, there's going to be a third equation, and that third equation is going to be we have to accommodate the constraint itself. In other words, the constraint being g x y itself being 0. Because even though we're using the gradient of g, ultimately we're constraining it to just the level curve when it's equal to 0. So if you use these three equations, how many unknowns are there going to be? Yeah, there's going to be x. We don't know x. We don't know y. We don't know lambda. How many equations do we have?
3.
Welcome to Algebra 2, ladies and gentlemen. We're basically just solving system of equations. So congratulations. This will either be the easiest thing of your life or the most difficult. So let's do an example, shall we? Example. So we want to find.
Is the third one g of xy equals 0?
I understand how that is impossible to read. Let me erase that.
That's gx of y, right?
G X Y.
Okay.
Yeah, it looked like an S that was trying to be a G that was used to be a 9. That's what it looked like. That's the issue. I did too much abstract mathematics. The symbols don't matter. I remember I didn't want to actually write out the variable that they were using, so I literally just did a squiggle on the page, and then I used the squiggle to stand in for that object. Let's see. Oh, and also RGB arithmetic, as you can create a binary operation that interacts on RG and B. And so essentially, you're just making these operation tables, and it's just colors. So I just have different colored highlighters, and then the operation itself could be a color. So you just have these strips of color that are spelling out equations, and you have systems of equations that form these little mosaics of color. So you can generate art through systems of equations. Okay, find the maximum and the minimum values of f x y is equal to 2x squared plus y squared plus 2. Everyone recognizes what this is because they studied their quadrant surfaces. Under the constraint let's constrain this to g x y is equal to
Oh, there's 2.
x squared
2.
plus 4y squared minus 4 equals 0. Okay, I'm going to highlight to you a few things before we actually dive into this problem. Quadrant surface. How do I just look at that and know it's a paraboloid instantly? Well, pretend like the y isn't there. If I were to graph that, what shape is that?
Parabola.
Okay, let's pretend x doesn't exist. What is that?
Parabola.
Wow, so it seems like as I open up along the axis, it's just a bunch of parabolas that are circling around. Okay, paraboloid. And then here is constraint. X is a square, y something square, yada yada, garbage, garbage, you complete the square. But this is what shape?
Circle.
Yeah. In the xy plane, this becomes a circle, level curve to 0. This is a paraboloid. So what we've done is we've got our surface existing. It's a paraboloid. And what we've done is instead of looking at the entire paraboloid, we're going to specifically only look at the values of the paraboloid we can get if we're to travel in the xy plane in this circular path, like a circular path. And so you can imagine we're going to be like going, as we go in that circle, we're going to kind of go up and then scoot back down. So yeah.
Isn't it it's not a circle, it's a 4 before the y.
Thank you. Yes, sorry. The path is elliptical, yeah. To accommodate probably for this. But the idea is you've got, and we're slicing something out that's going to be like.
Yeah.
So we're constraining the entire thing to this specific curve. And so there's going to be obviously extrema that we're going to find. And that's going to occur when the gradients, we're going to solve for it when the gradients are parallel. And that should make sense, right? Because gradient is telling you that's the direction of greatest increase. So intuitively, if you're parallel with where you're increasing the most on your surface, I would hope that is the maximum on your constraint, right? At any rate. So here's the algebraic interpretation of what's going on. Let's go down the laundry list. We first say, okay, well, Lagrange multipliers tells me that my gradient needs to be parallel, right?
Probably
I gotta stop using F and G because these are impossible to write, I swear. G, okay. Man, all right. And so the idea is, this is going to tell us that Fx is equal to lambda Gx, that Fy is going to be equal to lambda Gy, and then lastly, we need to accommodate for Gy here. So if we need to know Fx, Gx, Fy, and Gy, potentially we could just start by finding those, right? So what is Fx?
4x.
Yeah, 4x. Nothing crazy. What is Gx?
2x.
What is Fy?
2y. 2y.
Good.
Gy is 8y. 8y.
Y is 8y. Okay, so now let's see what's going on, right? If I'm going to do this first equation, so equation 1 in my system is the Fx is equal to lambda x. So we're going to do this one first. So Fx, plug and shove, equal to lambda times Gx. So Gx is this, and lambda is a constant. So we have 2 times that constant in the variable x.
So lambda equals
Equation numero dos. So we get Fy is 2y, so we could put that there. And then we're going to take Gy, which is right here, multiply that by lambda. So 8 lambda y.
For the first one is 4x equals 2, right? 2.
Yes. Too long. 4x is
Because it's 2x
Yeah.
times lambda, but lambda is a constant. And then the third equation is the constraint for accommodating our g, x, y is 0. Well, that's already kind of been given to us. So we just have x squared plus 4y squared minus 4 equals 0. Discord goes crazy in Cal 3, bro. Okay, and so what we're going to do now is this is a system of 3 equations and how many unknowns?
3.
So here's what we're going to do. I could just say this is trivial and obvious, but I recognize that it's probably a good refresher to go over this. So we're going to take this first equation, and what we're going to do is, what you shouldn't do is divide both sides by x. Do you know why we can't just divide both sides by x?
You eliminate terms.
Well, more like you can break laws of the axioms of the reals. X is allowed to be 0, you know. So if we're dividing by x, we're just claiming, yeah, division by 0 is chill. And then you'll end up with really broken solutions, and you're like, why isn't it working? Oh God! And he'll be like, because you broke the rules, and you can't divide by 0, it's undefined. So you came up with undefined solutions. So don't divide by x. That's the mistake. It's very tempting to want to start canceling stuff and slashing away, but that's only going to lead to problems. So the most I found efficient way and like clean way to do the algebra is to actually pretend and get both sides on one equation. And so here we do 2 lambda minus 4 times x equals 0. So factor it out, get all the x. There's a coefficient of x, it's a coefficient of x. So put it on one side. Because now you can accommodate not having to divide by 0 and you can get both cases. And this will take it down to only 2 cases, and 2 cases isn't bad to have to deal with. So here are the 2 cases you can get from this. Case 1 is easy. Let x be 0. And the cases I'll indicate with a little box so that we don't get lost with that. So that's case 1. And in the other case is what?
Lambda equals 2.
Yeah, lambda could be 2. So we could also have lambda is 2. That would also satisfy equation 1. So now that we've satisfied equation 1, we can kind of ignore it. We've taken all the information we can out of equation 1. And so that helps you know that the rest of what you're going to be plugging in will only involve either 2 or 3. And that's going to make the process a lot easier. So let's look at the tree. So if x is equal to 0, well, ultimately, we're just trying to find the xy coordinates of the location that are candidates for extrema. Okay? And so don't solve for lambda. The biggest mistake you can make here is thinking that you need to find what lambda is. Lambda is irrelevant. Lambda is necessary in the sense for the theorem that that's why we have parallel vectors. But in the scheme of things for the method, we're here just trying to find x, y pairs. So the moment that I've narrowed down one of my x's, am I going to worry about what 2 is right now? No, because I know that my third equation only has x and y. Well, if I know what an x is, then I can just isolate for y. And then that's going to give me my first set of points. So if I say x is equal to 0 here, plug into equation 3. And this is going to give me 0 squared plus 4y squared. 4y squared minus 4 is equal to 0. And so this tells us that y is equal to plus or minus 1. So in the case that x is equal to 0, you could end up with either y value. So both of these, and I'll put this in a circle, a candidate. Okay, that wasn't too hard, was it? Okay. Now, we've gotten our y point, or our y values from x. So x equals 0 case, nice, got it, okay? Now, lambda equals 2, well, are there lambdas here?
Yep.
So maybe by process of common sense, we just put it into the second equation. And so when we put that into the second equation, we get 2y is equal to 16y. Well, there is only one solution. And that is y is equal to 0. And so now we've gotten a case with a lambda, now to a case with y. And that's what we want, because ultimately we're just trying to find pairs of x's and y's. Lambdas, we don't care. We use the lambda to get to the next one, but ultimately we're after x's and y's. Yes, Sean?
So the reason why we can't do, like, when we get to equation 1, why we can't just repeat it for 2 is because lambda will give us two different values for that.
Yeah.
So we need to use one value.
And that's why, see, the case, doing it by cases is going to make sure you don't either double count or end up substituting in a place that you shouldn't have substituted, or accidentally dividing by 0, or making, etc. There's lots of little things that go into that. So, but anyway, now we know that this y is equal to 0, so the lambda has fulfilled its single task. Its single task was to get us to a y point, or an x point. And now, where are we throwing the y equals 0? Yeah, because this has been exhausted of its usefulness, and so we're into this equation again. So we get x squared plus 4y squared, so 4 times 0 squared, minus 4 equals 0. So x has to be plus or minus 2. Which gives us candidate points again. So if the y coordinate is 0 now, so if we have 0, then the x's that we could potentially have is plus or minus 2. So candidates. We have how many total candidates? It looks like 2, but it's really 4. A positive version and a negative version for both. Okay, thumbs up if the algebra is good. Okay. Not too hard. So, are we done?
No, we need to determine maximum.
Yeah. Have we found the maximum and minimum values of their function? No, we have not. What we've done is we found the candidates to actually test. We knew which candidates to find because of the Lagrange multiplier. But now the Lagrange multiplier has done its sole job. Lead us to the cases. Now we've just got to plug and check the case. Okay? So after you use the Lagrange multipliers to find the candidates, start plugging the candidates in. So f of 0 plus minus 1. And the reason I can do that is because I know that x is going to be squared. Or sorry, the y, well, both are going to be squared. So this is going to be 2, 0 squared plus or minus 1 squared plus 2. Do you guys recognize what this is? It's just the original function that we just talked about. So it's clear. And so that's going to be 3. And then f of plus minus 2, 0 is going to be 2 times x squared plus y squared plus 2. Do you see how showing work is really, really great? You know, it's good form. I don't necessarily agree with that word. Be more specific. Yes. So we have one maximum that it happens to occur twice. Yeah, and then we can find those 2 points. And then only one minimum that happens to we achieve it twice. There are not 2 maximums. So when you think about what's going on, then at some point we have to get to our maximum twice, and we have to get to our lowest elevation twice. So as you're going around this like piece of the parabola, you're kind of going up, and as you're turning around, you're scooping down again, but then you scoop back up, and so you get this kind of undulating. Yeah, it's like a roller coaster. So now you know roller coaster math. Next time you go to spend all of your engineering money on theme parks and such. So we would answer this as like we could say that on the max value of f is equal to 10 at, why do I even try to handwrite anymore? At plus minus 2, 0. Why can the math happen and then the English doesn't? It's not fair. Okay, in the minimum, of f is 3 at 0.
And so those two coordinates were just candidates, and we need to plug them into the equation to see which one was which, right?
Yep. Now, you know, I think it was like 2016 or whatever, is that ridiculous cartoon music video that went viral for a little bit, that Dumb Ways to Die? Well, I'll give you one of those. I'm calling a coordinate a maximum. I'm calling a coordinate a minimum. That's just Dumb Ways to Die.
It's so easy to solve.
You could sing the song to yourself and you catch yourself making that mistake in the Pearson. Just hit enter to be like, incorrect answer. It asks for the maximum value instead of the coordinate, you potato. And we're gonna go ways to. Okay, so yeah, max, distinguish between the max values and the points. Okay, now this was with 2 variables. Could you do this with 3 variables? Does the concept suddenly change? No. So this equation, that's why I like this form. Because so long as you know what the gradients are, because gradients are what?
Vectors.
So vectors have any number of components you really want. Now granted, am I going to make you do a system of 8 equations? No, I won't.
Pearson.
That's why Pearson does it. Pearson might. No, I think the biggest Pearson goes is 3 or 4, and it's not even that bad. I think the one that they go to 4, at least. Well, we also trimmed out some of the Pearson homework from when I took the class because there was a 24-part question in there.
We're still there.
Oh, it's still there?
Yeah.
Good.
24 parts.
So, are there
Here's one
questions?
point.
Guys, do you have questions about this example? Okay, so again, the algorithm is start with that first equation, get two cases, an x case and a lambda. Use the x case to skip down to your constraint, boom, done. You got your candidates. Then if you take the lambda case, use the lambda to plug into the other equation with the y's in it. That'll give you what your case should actually be for the y's, throw it into the constraint, you're done. Plug it into the function, okay? Yes.
This is for the homework. Can we get extra time on 15 seconds? Could we get
This is 15.8. Yeah. Oh, and speaking of 15.8, we're done with chapter 15. So the next lab, the lab that's due on Friday, is just going to be the last 3 sections of chapter 15. Those are the only concepts involved. So it'll just be, I think, 15 point, what is it? Isn't it 15.5 or 15.6 to 15.8? Yeah. So now you have everything you need to finish that lab too. Okay, a few things on D2L. Watch out for news items. I'm going to post something about. I want to treat you guys to Brahms on the Sunday before school resumes from fall break. So if there's people on campus then, we'll figure that out. And then also, there's one more thing I didn't want to forget to mention. Was yes.
Are the homework to do after homework?
Yeah. And the lab 6 will also be due after fall break too. Should you wait till after fall break to do lab 6? No. But yeah. Let's see. Oh, and then I'm also going to create a chapter 15 fall break kind of review guide, so that when you're going and studying over fall break, you don't have to look at chapter 15 as a whole and just go, that's a lot of stuff to review. Please catch up on Pearson if you haven't finished all the Pearson. I don't think you realize how heavy of a weight that is on the overall class percentage until you have like a 70 on it. And then you can get A's on all the exams and suddenly you're down a letter grade for no reason. Okay, so just do the Pearson. Was there a question? Okay, well, cool. You guys have a good time. I'll see you on Wednesday.